Hello. In this lecture, we are going to cover two additional circuit analysis techniques, namely nodal analysis and mesh analysis. In addition, we are also going to talk about the extension of these two techniques. So they are supernode and supermesh. So what is nodal analysis? So nodal analysis is a technique that you can use to find all node voltages in a circuit. And the branch currents can be found if resistances are given to you. And this is based on simple Ohm's law. So if I have V and I have I, or if I have V and I have R, I can find the current I. Or if I have V and I have I can find the resistance. Okay. So it's always knowing two variables out of three, and you find the third unknown. This nodal analysis technique is based on the principle of KCL. And as we discussed, KCL is based on conservation of charge. Such technique is ideal for circuits that have mostly current sources, as you will see in the subsequent examples. Nodal analysis is also based on the reference node. And as we discussed, a ground node or a ground reference is ideal for your reference node because this ground assumes a zero voltage. KCL equations are written for each node. So for example, if you are trying to solve for three unknown node voltages, then you will need to have three sets of KCL equations. However, for the reference node, you will not need a KCL equation for that. All the unknown node voltages can be found by solving a set of simultaneous linear equations. And you can use the following techniques to solve for the unknowns. For example, you can use Cramer's rule. You can use variable substitution or elimination, or metric row or column reduction, or you can simply use MATLAB. And perhaps I can add one more here. If you know how to program in your calculator, you can use your calculator to solve for those unknowns as well. Let me first walk you through the procedure on how to use this technique. So number one, you will have to select the ground node of the circuit. And I'll show you how you can identify the ground node in the examples given later. Number two, you're going to define the unknown node voltages. And those are the ones that you're interested in. And in particular, those node voltages should not be fixed by voltage sources. Number three, you're going to write KCL equations for each of these nodes. Number four, KCL equations are written assuming all passive element currents are flowing out of the node. And I'll illustrate this point using examples later. Number five, source current flow directions are indicated. And number six, you need to solve for all the KCL equations simultaneously. So if you have n equations, then you will have n unknown node voltages. So I'm going to go through some examples first, and then we will come back to this procedure so that you understand what this means step by step. So this is the first example. So I have two current sources, and I have 3 resistors connected in this way. So over here, I'm going to first select the ground node. So in this case, I'm going to put my ground on the bottom here. And the reason I chose this to be my ground is because all these branches are converged to this one common point. And this one common point is the best place for me to insert this ground without disturbing the nature of this circuit. And I can use this as my reference so that if I want to calculate or if I want to find VA, this no voltage, then all I have to do is I take this VA minus this 0 volts. In other words, voltage drop across this 2 ohm resistor is simply VA, since this reference node voltage is equal to 0. So the voltage drop, which is the potential difference between this node voltage and this node voltage, is the delta between VA and 0, which is simply VA. So I have this as my ground reference. And I'm going to choose, or I'm going to identify my node voltages. And my node voltages are here and here. Okay. And notice that this point, node VA, is the same as this node, and it's the same as this node, because this is a short. So a short means the potential along this short always the same. So this point here is VA, this point here is VA, this point here is VA. Now similarly, this circle over here is VB, which consists of this dot, and this dot, if you want. So all these points will give you the same voltage, VB. So then once we found VA and VB, then we know what is the voltage dropped across 2 ohm resistor and 7 ohm resistor respectively. So that's basically the motivation behind doing this exercise. I wanted to find what is the node voltage here, node voltage there, so that I can calculate or I can find what is the voltage dropped across 2 ohm and 7 ohm. And given resistance, 2 ohm, 6 ohm, and 7 ohm, I can find, therefore, my current. Okay. So let's see how this nodal analysis works. So I'm going to pick one node, start. So we have defined the unknown node voltages as in step 2. And in step 3, I'm going to start writing my KCL equations. So I'm going to first start with this VA node. Okay. So I'm going to say at node VA, and using KCL, I know that all the current entering the node has to be equal to 0. In other words, the sum of all the currents leaving the node has to be equal to 0. Equivalently, I can also say the current entering this node has to be balanced by the currents leaving the node. If you go back to this page, this procedure, you will see that KCL equations are written assuming all passive element currents are flowing out of the node. Now, this is just the way I prefer to do my nodal analysis. I assume all the currents flowing out of the node. My passive sign convention is my passive element current for the direction of this current flow. You can also assume the opposite. You can say all passive element currents are flowing into the node. That is perfectly fine. But you have to be consistent here. So in this case, I'm going to show you two different ways of looking at this step number 4. So at node A, if I assume the current flowing out of the node, then the current flowing out of the node, for example, this current going to the right, flowing out of node VA is going to be the voltage drop across this 6 ohm resistor divided by this 6 ohm resistor. So the current going from left to right can be found by voltage difference, which is VA minus VB, okay, divided by 6 ohm. Okay, so it's V over R. It's not just VA divided by 6, it's not just VB divided by 6, but it's the difference. But looking at the potential difference here. So the voltage drop across 6 ohm resistor divided by the 6 ohm resistor. So that's my first term over here. So again, this term accounts for the current flowing from left to right. This is the current assumed to be flowing out of the node. This current over here is simply equal to VA minus 0 divided by 2. By the same token, I want to find potential difference or the voltage drop across this 2 ohm resistor divided by this 2 ohm resistor. So the voltage drop across this resistor simply is equal to VA minus 0. VA minus 0. And 0 is because I have this reference node, my ground reference, divided by 2, right? So again, I'm using Ohm's law. So I take voltage drop divided by 2 ohm resistor. So that I will get current going down this way. And again, this current is flowing out of the node. Okay, so if you look at this node is shared by 3 branches. So since I have 3 branches, so you expect to see 3 terms. So we have 1, 2, and we still need 1 more term. Okay, so now if I do the same, if I assume the current is leaving the node, then I need to know what is the current flowing from right to left, or flowing out of this node going to the left. Now, since this current source is fixed and the direction of this 1 amp current source is flowing upward, so in order to represent the current going from right to left and go down, this current is simply flowing in the opposite direction of this guy. So if this is 1 amp flowing up, then flowing down is going to be minus 1. Opposite direction. So this minus 1 amp going from right to left is my third term. So I have 1, 2, and 3. Now, in this particular equation, if you look at the way I wrote this equation number 1, you see that I put these 2 terms on the right. And these 2 terms corresponds to the current flowing out of the node. Whereas this term on the left corresponds to the current entering the node. As far as KCL is concerned, this equation perfectly satisfies the KCL law, right? Because as we discussed, we know that the current going into this node has to be balanced by the sum of the currents leaving the node. So the current going into the node is actually how much? It's 1 amp. 1 amp is going up to the right and is going into this node, while the current VA minus VB over 6 is leaving the node. Same thing for this current VA minus 0 divided by 2. Okay, so this is one way to represent this equation, okay, based on KCL. And of course, strictly speaking, if I want to follow step number 4, assuming all passive currents are flowing out of the node, this is what I'm going to do. I'm going to rewrite over here. Okay, I'm going to say VA minus VB over 6. This part is the same, right? Because this is the current flowing out of the node, plus VA minus 0 divided by 2. So again, this is the current leaving the node, right? So this term remains the same. Now over here, right, one exercise that we did earlier, if I want to represent the current leaving the node, instead of 1 amp going into the node, I need to attach a negative sign. Okay, so I'm going to say plus -1. And keep in mind, all these terms, all these currents leaving the node has to be summed to 0. Right, there's this equal sign here, right, as always. So now if you compare this equation number 1 and this equation, they have exactly, well, they are the same mathematically, right? Because I can move this -1 over to the other side. And now if I do that, then these two equations are exactly identical. Okay, so depending on how you want to manipulate your equation mathematically, right, as long as you satisfy KCL, then you're okay. Okay, so even though I say flowing out of the node, right, you, instead of making this -1, right, you can simply just leave it on the left-hand side, okay, or the other side of the equal sign, so that you don't have to attach this negative sign. Okay. All right. So that's that for node A. Let's go to node B. So for node B, I'm going to do exactly the same. So now I'm over here. So I need to consider again 3 currents leaving the node. So by the same token, I have VB minus VA, the voltage drop across 6 ohm divided by 6 ohm. So that's this term over here. Plus VB minus 0 divided by 7, which is the current flowing down this way. Okay. The current flowing out of node B going down this way is simply equal to 4 amp, as indicated by this current source pointing downward. So this is 4 amp. So if I want, I can move this 4 amp to the other side of equal sign, right? So that such that I have a negative sign over here. And the reason I'm doing this step is so that I can make this equation in a similar form to my equation number 1. Okay. So that when I solve for the unknown node voltages, I can just do elimination. And just use elimination. Okay. Okay. So one assumption here, the currents are leaving node A and node B. That's my assumption here, right? Unless they're imposed upon me. In this case, this current and this current, they're imposed upon me, right? These are fixed. This and this are fixed. Okay, the direction of this 1 amp and 4 amp are fixed. This is set by the problem. Okay, so assuming you have found your VA and VB. Now, if I ask you to find the voltage drop across 2 ohm and 7 ohm, then now you know that this voltage across 2 ohm is nothing but just VA, right? Because this voltage is simply VA minus 0, and that's just VA. Then similarly over here, VB minus 0, so this voltage is simply just VB. Okay. And if I ask you to find the current flowing through this 6 ohm resistor, then once you know VA and VB, you know how to calculate I, right? This is what we did earlier. So I is simply VA minus VB, voltage drop across 6 ohm resistor divided by 6 ohm resistor. Ohm's law, right? V is equal to I times R. Okay, so this is example number 1. So now if I go back to this list, right? So we were talking about step number 4, assuming the currents are flowing out of the node, right? And number 5, right? This is pretty straightforward because we know that the source current flow direction are set by whatever is given to you, imposed upon you, right? And number 6, after you have written all the equations, you just have to solve for the unknowns. So I hope these steps here are clear. Okay, so let's do the next example here. So in this example, I have one voltage source, one current source, and a couple of resistors. And again, I need to find some node voltages. And for just to make the problem a little bit more fun, more interesting, I'm going to move my ground reference. Instead of putting it over here, okay, I'm going to put it over here. And there's a reason why I chose my ground reference over here, okay? And the reason will be more apparent when we talk about super node or super nodal analysis. So I'm going to put my ground reference over here. So that means the unknown node voltages will be node VA, node VB, right? This is one node as well, and node VC. Okay, so I have 1, 2, and 3, and this guy here is connected to my ground reference. So this, strictly speaking, is not considered as an unknown node voltage, right? Because we know that by inserting the ground reference over here, we assume this node here is equal to 0. Okay, ground reference, 0 volts. Okay, so similarly, we have to find VA, VB, and VC using KCL. Okay, so let's look at node C first, right? This is perhaps the most straightforward one to look at. So by inserting my ground reference over here, without doing any calculation, I can already deduce what VC is. Okay, so how do you do that? Okay. So I'm going to slightly rotate this. Just focus on this part here. Okay. I'm going to redraw it over here. So this is my VC node. So this is this node. I have 10 volts, right? So that's my 10 volts over here. And this piece here, right? This part here is connected straight to my ground reference. So I'm going to put a ground here. Okay. So immediately, I hope you can see how much this VC voltage should be, right? If this is 0 volts, this here is 10 volts, then how much should VC be? VC should be 10 volts, right? You see that this is my ground, and from negative to positive, that means I have a voltage rise of 10 volts. So from ground, I rise up by 10 volts, and therefore my VC has to be equal to 10 volts. Okay. So at node C, VC is simply equal to 10 plus 0, or 0 plus 10, okay, which is 10 volts. Right, and this can be done by inspection. So again, this is my ground node, rise up by 10 volts, VC is equal to 10. Alternatively, you can also show it in the other way around. You can say, well, I have this voltage, right? So VC is some unknown voltage. So VC minus 0, which is the potential difference, should be equal to whatever this voltage source is, which is 10 volts. So VC minus 0 is equal to 10. So therefore, VC has to be equal to 10. So that's another way to figure this one out. So we have node VC. So this is one of the node voltages that we need to find. And how about VA? So at node VA over here, I'm just going to follow exactly the same technique that we discussed. So VA minus 0 divided by 2, right? I'm assuming current is flowing out of the node. So that's this term over here. VA minus 10 divided by 2, where is 10? Well, now we say VC is equal to 10 volts, right? We calculate it over here. So VA minus 10 divided by 2, that is the current flowing to the right, right? Again, that is assuming the current is leaving the node, right? It's going from left to right. This term over here. And remember, KCL says the sum of the current entering the node has to be equal to the sum of the current leaving the node, right? So over here, I spot this current entering the node. So this Φm is flowing into node VA, okay? So instead of saying plus minus 5, I'm just going to put it on the other side. I'm going to say 5 on the other side of the equal sign. So this 5 indicates is the current flowing in, right? So entering the node, and this has to be equal to the current leaving the node, which is taken care by this term and this term, which is this current and this current. And this is my, you can say this is equation number 1 or equation number 2, right? Since VC is already found, right? So I'm going to say this is my equation number 1. Okay, so at node VB, which is this node here, by the same token, VB minus, so I'm going to start with this term first, VB minus 10 divided by 8, which is the current flowing out of the node. This is my node flowing out. Okay, so that's this term over here. VB minus 0 divided by 4. 0 because I have this ground reference here, and ground reference assumes 0 volts. VB minus 0 divided by 4 plus 5. And this 5 is the current that is imposed upon me. So this current is already defined to be flowing out of the node, right? So that's good. So I just need to add plus 5. Sum of all the current leaving the node is equal to 0. On the other side of the equal sign, I have 0. This is my equation number 2. And you just need to solve for VA and VB. The rest is just math. Next example. I have, again, multiple current sources. In this case, I have 3, 1M, 3M, and 8M. I have a couple of nodes, node VA, VB, and VC. So to find, so the question asks you to find also IX and VY, where IX is the current flowing through 75 ohm resistor, and VY is the voltage drop across the 75 ohm resistor. So before we can find Ix and Vy, we have to know Va, Vb, and Vc. And this is pretty standard, right? Because once we know all these node voltages, then we can go ahead and find the current. If I gave you resistor, right? Or I can find the voltage because I know the voltage drop across this resistor simply is the potential difference between this voltage and this voltage, right? So I can do a lot of things if I know the node voltages. Okay. So again, I'm going to name it VA, VB, VC here. This node here is the same as this node. This node here is the same as this node. Okay, so this is considered one node. This is considered one node. Similarly over here, this is considered one node. For this node B, there are 4 branches, as you can see. One here, one here, one here, and the other one here. These 4 branches all share the same node VB. Okay, so let's first look at node VA. So at node VA, what do I have, right? So VA minus 0, right? So this is my ground reference, right? So this makes sense because this is the common node to all these branches, right? So very clean here. So I'm going to take this as my ground reference. So VA minus 0 divided by 50. VA minus 0 divided by 50. So that's the current going down. Plus VA minus VB divided by 75. The current, basically your Ix, right? This is Ix. This here is Ix. Ix. And then plus -1, right? So if 1 is flowing into the node, then -1 is flowing out of the node, right? So in this case, I chose to write it this way. So -1, right? Plus this current plus this current is equal to 0. And that is my first equation. At node B, remember, we need to have 4 terms. So VB is equal to 3M, which is this current flowing out of the node. This is imposed upon me, right? So the direction has been indicated by this current source. Okay, so this is 3 flowing downward plus VB minus VA divided by 75, which is this current going this way, and this is in fact minus of Ix, right? Because Ix and this current are flowing in the opposite direction, so therefore this current has to be equal to minus of this Ix. Okay, so VB minus VA divided by 75 plus VB minus 0 divided by 10, which is this current going down here, plus VB minus VC divided by 75, which is this current going here. So I have 4 terms, 1, 2, 3, 4. The sum of all this current should be equal to 0, right? I still need to follow KCL. Okay, so this is my equation number 2. The last equation at node C over here, VC minus 0 divided by 100 plus VC minus VB divided by 75 plus -8 in sum to 0. 3 equations, 3 unknowns. So for VA, B, and C. Now, assuming we have done the math behind the scene, VA is equal to 37, VB is 17, VC is 352.76 volts. Based on these numbers, we can go ahead and calculate Ix and Vy. So first of all, Vy is equal to the difference, the potential difference between node VB and VC. So you see that I have plus here and minus there, right? So this is the way I define my Vy. So to calculate Vy, I need to take the voltage at VB minus the voltage at VC. VB minus VC now gives me minus 335.4 volts. So in other words, this guy here is minus 335.4 volts. Okay. If I don't like this minus sign, what I can do, right? Equivalently, I can say plus minus, I put 335.4 volts. This and this are the same. If Vy is minus 335.4, then that means my polarity has to be plus on the left and minus on the right. If I don't like this minus sign, then I have to reverse the polarity. So I can get rid of this minus sign, but I need to change the polarity. Plus becomes minus, minus becomes plus. Okay, and these two are equivalent. For Ix simply is equal to VA minus VB over 75. So that's over here, 0.26 M. Okay, so now let's move on to the next topic, which is supernode. Supernode is considered as an extension of the nodal analysis that we just studied. So let me give you one example to show you when and why we need to learn supernode, right? Why is it that the regular nodal analysis doesn't work, okay, in this case? So in the setup below, I have two current sources, I1 and I2, and I have two resistors. And it's very natural for us to set our ground reference over here because this is a common node that is shared by all these four branches. But now you notice that between node VA and VB, I have a voltage source. And this voltage source is going to create a problem. Now, if you look at this voltage source, right, we call this a floating voltage source because neither end of this voltage source is connected to the reference node. Where's my reference node? My reference node is over here. But in this case over here, neither end of this voltage source is connected to ground. So in such case, this voltage source is said to be floating. A floating voltage source is one for which neither side is connected to the reference node. So what seems to be the issue with this floating voltage source? The problem is, unfortunately, we cannot write KCL at node VA or VB because there is no way that we can express the current flowing through this voltage source in terms of VA minus VB. Now remember, for us to write an equation, or for us to represent this current flowing out of this node, we take VA minus VB divided by some resistor. Right? Assuming this resistor is connected between VA and VB, right? Just like before, in the examples before, I can simply calculate this current by taking VA minus VB divided by whatever this resistor is. Right? But in this particular setup, we don't have this luxury, right? Because this guy here is a voltage source. This is not a resistor, right? So I can't just simply take VA minus VB divided by whatever this guy is, right? We can do that. So in that case, we don't know what is the actual current flowing into this voltage source. We have no easy way to express this particular current flowing out of this VA node. Okay. So instead, what we're going to do here, we're going to define something called supernode. This is when supernode comes to rescue. So what is a supernode? So a supernode is a chunk of circuit that contains nodes A and B. If I circle this guy like this, encompassing both node A and B, this is my supernode. The chunk of the circuit that contains both nodes VA and VB. And this is my supernode. It consists of two nodes, not just one. Not just VA or VB. It's both VA and VB. So in such case, I can go ahead and express this, or I can go ahead and write a KCL for this particular node, for this supernode. Okay. But then you're going to say, well, wait a minute. If I write an equation, KCL equation for this supernode, and yet we have two unknowns, we still have two unknowns, that part will not change. Those two unknowns are still VA and VB. But if we are just going to write an equation for this particular supernode, then how are we going to solve for VA and VB, right? Shouldn't we have two equations so that we can solve for two unknowns, right? And right now we only have one equation. How can we solve for two unknowns with just one equation, right? So then what we have to do is we need to come up with another equation, and that equation has to somehow relate VA and VB together. If we can generate another equation in terms of VA and VB that hopefully describes the relationship between VA and VB, then we have two equations now, right? One equation is still this KCL for the supernode, and the other equation is generated based on the relationship between VA and VB. Okay, so I need that additional equation, okay, relating between these two nodes. Okay, let me give you one simple example here. If this voltage here is 10 volts, right, numerically, this voltage source is 10 volts, I can write an equation that relate VA and VB together. How do I do that? Well, this is something that we did a few minutes ago, right? If I were to rotate this guy a little, right, and then this is my VB node, this here is my VA node, and this is 10 volts. So what do you do here? Remember the voltage rise and the voltage drop discussion that we had earlier? From this point, this is the node associated with the negative sign, right? So we know that this is going to be at lower voltage. So in this case, I have a voltage rise from VB to VA by how much? By 10 volts. Right, this voltage rise is going to be 10 volts. I go from negative to positive, so I know it's a voltage rise. Okay, so in other words, VB, lower voltage, plus 10 volts, right, voltage rise is equal to VA. Okay, so this is my second equation that is used to relate these two nodes, right? And of course, you can also say this way, VA minus VB is equal to 10 volts, right? The voltage drop, right? This is voltage rise, this is voltage drop, right? And these two are the same. Right? If you rearrange, you're going to see they're the same, right? So you take VA to the other side, so VA is going to be 10 plus VB. Okay, so that's how we got second equation so that we can solve for two unknowns. Okay, I'm going to jump straight to the first example to show you how this works. Okay, so I have two sources, one voltage source and the other one is current source. 2 ohm, 2 ohm, 4 ohm, and 8 ohm. The first thing you need to do is assign your reference node, ground reference. Okay, so again, I'm going to pick this as my ground, right? This seems to be a very clean node that is common to all these three branches. Okay. But if you look closer, I have this 10 volt here, and this 10 volt is simply just floating because neither end of this 10 volt is connected to my reference node. Floating, right? So if you look at this one side is Vx, the other side is Vy. If you look at this voltage source, one side is to VA and the other side is to VB. Neither end is connected to my reference node. So this is said to be floating. Same as this guy. Okay, so in that case, I know I need to use supernode. So I'm going to circle this, okay, and I'm going to call it supernode. And notice that even though I say I circled this, but in reality, right, it's basically this, including no Vx and Vy. Okay. Okay, so the next thing is we need to write an equation to relate Vx and Vy, right? So we are just going to do what we just did. So by inspection, I have minus here, plus here. So the plus is connected to Vy, minus is connected to Vx, higher potential, lower potential. Vy minus Vx plus minus the negative, right, has to be equal to 10 volts. So Vy minus Vx is equal to 10. Therefore, Vy is equal to Vx plus 10. Right. You can call this equation 1 if you want, but I think I assign equation 1 over here. So if you want, you can call it equation 0, right? But you will see that I don't need this one because I'm just going to plug it in directly over here in the first equation. Okay, so this is one equation in any case that you need in order to solve for the unknowns. So the next thing is I'm going to write a KCL equation for this supernode. Okay, so at supernode, and remember this supernode does not contain just Vx or Vy. It contains both. It contains both Vx and Vy. Okay, I'm going to start on this side first. So Vx minus Vz. Okay, so this is Vz. Okay, so Vx minus Vz divided by 2. That is the current flowing this way. Okay, Vx minus 0 divided by 4. This term here, the current flowing down this way. Okay. As far as Vx node is concerned, I'm done already, right? Because I have identified the two currents flowing out of this Vx node, which is part of my supernode. Okay. So now I need to move on to the next node, which is Vy node, right? So again, supernode consists of both Vx and Vy. I'm done on the left. I'm going to move to the right. So Vy node, Vy minus 0 divided by 8. Okay, but what is Vy? Vy from earlier is equal to Vx plus 10. So that's why I plug this in here directly. So this is Vy divided by 8. Okay. Plus this current flowing to the left, Vy minus Vz divided by 2. And what is Vy? Vy is nothing but Vx plus 10. Vy minus Vz divided by 2. Vy minus Vz divided by 2. So now I can call this equation 1. Okay. But we are not done yet, right? Because I still need to deal with this Vz. So what is Vz? This one is simple, right? This is just a node by itself. So Vz minus Vx divided by 2 plus Vz minus Vy divided by 2 plus negative 5 is equal to 0. Three terms, because I have 3 branches. This current, and this current. Okay, 1, 2, and 3 sum to 0. This is equation 2. So 2 equations, right? And we can solve for Vx and Vz. Okay, and from there you can figure out what is Vy, right? Okay, so let's move on to the next example. Okay, so in this example, again, we're going to use supernode. Okay, so I'm going to assign my ground reference on the bottom here. And I need to first identify my supernode, right? And clearly you see that this voltage source, one end of this voltage source is connected to my ground reference. So this guy here is good, right? This VA node is considered as the regular node. However, this voltage source over here, neither side of this voltage source is connected to the ground, right? This is not a ground. This is not a ground because I have 6 ohm in between this node and ground. Right? So this guy here has to be considered as my supernode. Okay. So by inspection, VA, this is VA node, is equal to 10. Right. So 0 volts raised up by 10 volts is my VA. So VA is equal to 10 volts. Okay, so basically without doing anything, right, just by inspection, I can already figure out what this VA is. And in fact, VA is one of the variables that you need to find. It's that simple, right? If you know how to eyeball it, do it by inspection, you can figure, the simple things out first. Okay, so then the next step is I need to, since we have supernodes, so we need to have this equation that relates VB and VC. So in other words, the relationship between VB and VC is as follows. So VB minus VC plus and minus, right? So positive minus the negative, VB minus VC has to be equal to 5. So therefore VB is equal to VC plus 5. And VB minus VC simply is VBC. Okay. Okay, so this is the equation that describes the relationship between VB and VC, and we need this. Okay. So now I can write equation for this supernode. Okay. So for this supernode, you look at the way I circle the supernode, right? So VB and VC are both part of my supernode. So in other words, the supernode consists of node VB and VC. So I'm going to start with this VB first. So VB minus VA divided by 2, which is the current going to the left, plus VB minus 0 divided by 8, which is the current flowing down, plus, right? So we are done over here, right? Because as far as this node is concerned, we only have 2 branches that we need to deal with, this and this, right? And that accounts for this term and this term. So now I need to move on to the next node, right? Which is still part of my supernode, right? So node VC minus 0 divided by 6, which is this guy. Vc minus Va divided by 4. Right? So that means this current is going down, going back this way, up and to the left. So Vc minus Va, where Va is 10 volts by inspection, right, from earlier. So Vc minus 10 divided by 4, sum all of this current to 0. We're still following KCL. Right? Don't forget, we always using KCL in this type of analysis. Okay. This is equation number 1. Okay. And the rest is just math. Based on this, you can already solve for the unknown Vc and therefore Vb, right? Since Va is already found by inspection, right? And if you know Vc, then Vb can be found easily, okay, from this relationship. Okay, so that's that for this example number 2. Example number 3. I'm going to show you 2 different approaches. One by using regular nodal analysis, okay, and the second approach is by using supernode. And of course, you can be your own judge to see which one is easier. It turns out that for this particular problem, right, it's possible for you to solve using regular nodal analysis, and perhaps this is a little bit more straightforward for some of you. Okay, so let's see what this problem looks like. Okay, so it looks fairly interesting, right? A little bit symmetrical, okay, but not quite, because I have voltage sources on the bottom here, right? But you see, I have this resistors, going like across. Resistors here, 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 and there as well. Okay, so first of all, we need to assign our ground reference. Okay, so I'm going to choose this here as my ground reference, and I need to name my unknown node voltages first. So I have node VA, VB, VC, and VD. Okay, this over here is not strictly speaking a node, right? Because this is 0, right? This is has nothing to do with node VA, VB, and VC. Okay, so this is my reference node which I picked. Okay, so at node VA, can start writing my equation for this node. So VA minus VB, which is the current flowing to the left, divided by 8, plus VA minus 90. Right? So notice that this point here has a voltage of 90 volts. Why? Because this here is 0 volts, rise by 90 volts. I have 90 volts here. So this node minus this node voltage, which is 90 volts, divided by 8 is the current flowing down this way. That's why I have this term. VA minus VD divided by 4, current going up this way. Okay, 3 branches, 3 terms. Sum all these currents to 0. This is my first equation. Simple enough. Speed up a little bit. And now VB, what do we have? VB minus 0 divided by 16. VB minus VC divided by 20. VB minus VD divided by 5. VB minus VA divided by 8. 4 terms. Yes, I have 4 branch currents. 4 currents going through each branch. Okay, and this is my second equation. See what's the next node? VC, right? So VC, I have VC minus VB divided by 20, VC minus VD divided by 10, VC minus whatever this voltage is divided by 4. And whatever this voltage is simply minus 60 volts. This is my ground. From this ground to this node, the difference from here to there has to be 60, right? So 0 minus 60 is going to give you minus 60. You take the plus minus the negative sign, right? So 0 minus whatever this voltage is has to be equal to 60. So this voltage has to be minus 60. Okay, so where is it? Yeah, so VC minus 60 minus negative 60 divided by 4 is equal to this current. Okay, so again, 1, 2, and 3 terms. Okay, sum to 0. This is my equation number 3. Lastly, node D over here, VD minus VB divided by 5, VD minus VC divided by 10, VD minus VA divided by 4. 3 branches. Correspondingly, I have 3 terms. 4 equations, 4 unknowns. Now you can go ahead and solve for VA, B, C, and D. Okay. Standard procedure, right? So it's very standard once you know how to do it. Right? You just need to follow the procedure step by step. Write equation for each node. Come out with this equation, right? Depending on the number of nodes, right? Write those equations down, and then you can solve for the unknowns. Of course, you have to be careful if there is a supernode. So I'm going to show you in the second approach where this problem can also be solved using supernode. I'm going to show you how to do that. So instead of assigning my ground reference over here, okay, so I'm going to assign this reference over here in the middle. So this point here used to be, if I remember correctly, no VB, right? So now it's going to assign this to ground. Okay, so this is now my ground reference. And instead of using A, B, C, D, I think I use X, Y, Z, and A over here. Right? Change the variable a little bit. That's okay. All right. So now, after I reassign my ground reference, the problem, even though the circuit is the same, but then I basically changed the way I solve this problem a little bit, right? So I can no longer use the regular nodal analysis, right? Because now you see these 2 voltages are floating. Why are they floating? Well, neither end of this voltage source is connected to ground. This is not 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 connected to ground. Okay, where's my ground? This is my ground. Okay. So I'm going to go ahead and start writing equations for node VA. Okay, so VA minus VY divided by 10 plus VA minus 0 divided by 5 plus VA minus VZ divided by 4. This is equal to 0. Okay, so far so good. And now Z over here, VZ minus 0 divided by 8. So VZ minus 0 divided by 8, right? This term in the middle, plus VZ minus VA divided by 4, which is this guy over here, plus this current going down, which is VZ minus whatever this voltage is, divided by 8. And what is this voltage? Well, from before, remember, before we assign this node here as the ground reference, right? So this here is simply 90, right? But now I assign this to be Vx, so there's some offsets here, right? So Vx plus 90 is this node. So for this term, I need to take Vz minus whatever this voltage is, which is Vx plus 90, divided by 8. Okay, and this altogether will sum to 0. I'm still following KCL, right? Nothing has changed. And no Vy over here. Okay, a little. Vy minus Va divided by 10. Vy minus 0 divided by 20. Vy minus whatever this voltage is divided by 4, right? So by the same token, we know this voltage here is simply Vx minus 60, right? Again, I have this offset, so I need to account for this offset. Okay, 3 branches, 3 terms, pretty standard, right? Save the best for last. Supernode. This is my supernode, right? Floating voltage sources, right? And in this case, I have 2 voltage sources, and that's fine. Okay. So for this supernode, if you look at this red circle, right, this guy encompasses this node, and this node, this node, this node, and this node. It's really this node, these 2 nodes, plus this node, which is Vx node, right? Because this and this and this are the same, right? So I have 1 node, 2 nodes, and 3 nodes. Okay, so this supernode consists of 3 nodes, not just 2, right? Slightly more advanced, right? So because before, in the previous examples, this supernode consists of only 2 nodes, right? But now we have 3, 1, 2, and 3, right? Including this Vx, right? Because this Vx is also part of my supernode now. And why is this? Why is Vx part of my supernode? Well, this Vx is still part of this node, right? And this node is still part of my floating voltage source, so I have to account for this, right? Okay. All right, so let's do our analysis here. So I started from this node here. So Vx minus 60, right? This is the node. So this minus Vy divided by 4. Okay, so that's this term. And since there is only 1 branch, okay, associated with this node, so basically I'm done over here. So now I'm going to move to the next sub-node, if you will. Right, this Vx node can be considered a sub-node within supernode. Vx minus 0 divided by 16. So what I'm doing is capturing the current flowing out of the node, including this one as well. So for this one, this node, Vx plus 90, take this minus Vz divided by 8. This minus Vz divided by 8. This minus Vz divided by 8. You sum all these things to 0, okay? Again, following KCL. And now you have 4 equations, 4 unknowns. So you can go ahead and solve for Va, X, Y, and Z. Okay? And I invite you to try this out, right? Just to make sure the answers you obtain are the same as the ones that we